Hello everyone, I'm Maitre and today I will be presenting our CVPR 2026 paper VibeToken, where we try to scale the 1D image tokenizers and autoregressive models for dynamic resolution image generations. Diffusion models are the community and the production standard for the scaling or image generative solutions for the users, mainly because the diffusion models are easier to scale to arbitrary expectation high resolution. While the autoregressive models are gaining attention these days, but most of the existing solutions are trained on fixed low resolutions such as 256 and 512. And scaling these autoregressive models to higher resolution and arbitrary aspect ratio require significantly more computational cost. Basically, to generate the 1024 x 1024 resolution images using LlamaGen, we require 11 trillion flops per forward pass, which is very not feasible at all. And to improve the autoregressive model to support the arbitrary resolution generation, we propose a completely novel philosophy. What if we push all the resolution handling into the tokenizer rather than the generative model? Can we encode any resolution images into a fixed small number of tokens and decode them back? If we can make this possible, then we can train the autoregressive generative model on the fixed small low token budget. And tokenizer shoulders the scaling of the resolution. Because of this, inference cost remains constant and pretty low. And to make this happen, we propose the first resolution-agnostic 1D tokenizer, VibeToken. Existing 1D tokenizer has built on top of the transformer-based encoder-decoder layer, but these transformer layers are not very supportive of the arbitrary resolution and aspect ratios. And to do this, we improve the four different aspects of this architecture. Specifically, first we improve the position embedding and propose a dynamic grid position embedding. And second, we improve the patch embedding, which can encode the end resolution image into any arbitrary length number of tokens. And because of these two pieces together, we can cut the flops by almost 3x, while still improving the generalization and the reconstruction FID on high resolution. Third, to improve the decoding of the any arbitrary resolution aspect ratio, we further extend the decoder to adopt the adaptive decoder resolution. And because of this, we get the native 4x super resolution abilities while still retaining the state-of-the-art performance. To this end, we train both encoder and decoder model to support the variable length encoding. Basically, encoder can encode the any resolution aspect ratio images into 32 to 256 tokens without degrading the performance at all. As a result, we get the best Pareto optimal performance and get the state-of-the-art results. To train the vibe token, we basically mix all three different recipes: resolution mixture, aspect ratios, and the length and the quantization. We train our model only on the 256 and 512 resolution budget, and we still observe that it generalizes up to the 1024 resolution without requiring any resolution-specific fine-tuning. As a result, Vibe token is the only 1D tokenizer that can support any arbitrary aspect ratio and the resolution, and while still maintain the competitive performance compared to the 2D tokenizers. And while 2D tokenizer requires 4K tokens to encode 1024 resolution images, our Vibe token can encode the 1024 resolution images as low as 256 tokens, and even further can be compressed to as low as 6432 tokens. Next, we use this pre-trained Vibe token tokenizer to train the autoregressive model, where we call this model a VibeToken-Gen. VibeToken-Gen is trained to only generate 64 tokens, and all the resolution-based decoding, pixel decoding is handled by the Vibe token. As a result, we don't need to train the generative model to support the 4K, 10K, or 16K tokens for high resolutions, but only 64 token based small autoregressive model is enough to generate the high quality images. In this slide, we can see that the VibeToken-Gen can generate arbitrary aspect ratio and high resolution images with just 64 tokens and just ImageNet 1K budget. As a result, VibeToken-Gen is the only autoregressive model that can support any arbitrary expectation and high resolution generation. and while still achieving state-of-the-art performance compared to the diffusion-based models. When we try to compare the VibeToken-Gen with the corresponding autoregressive baseline, LlamaGen, we observe that the LlamaGen increases the computational budget and the latency quadratically as we increase the resolution. For instance, LlamaGen requires 30 seconds to generate 1024 resolution images, while the VibeToken retains the constant computational cost and requires only 0.5 seconds to generate the images. The key takeaways are resolution-agnostic tokens unlock autoregressive models for production, and VibeToken is first 1D tokenizer to natively support the arbitrary resolution and the aspect ratios. As a result, for the first time, autoregressive model closes the flexibility gap with the diffusion models.